Okay, we're going to look at number 4 in section 3.8. We're to calculate the derivative with respect to x. So, of course, we've got the equation here that revolves y and x. So we're really looking for dy dx. Now, we do want to do this using implicit differentiation. So my instructions would be find dy over dx using implicit differentiation. It is important to note the derivative we're looking for because we could also find dx dy, the derivative of y with respect to x. Dx dy, the derivative of x with respect to y, excuse me. So pay close attention to what we're looking for. Now, this one you actually could solve for y. It's not that hard to do in this equation, and then we can explicitly solve for the derivative. We would have y given explicitly, and we would just use our rules, normal rules of derivatives to do that. But we're going to show you how to use implicit differentiation, which is what you're mainly doing right in this section. So how does that work? I'm going to take the derivative with respect to x of both sides of this equation. And I want to remember that when I do so, right, I'm taking the derivative with respect to x, but y is some function of x, right? In fact, you can solve for y here and actually get y as a function of x, which we're not going to do, but y is a function of x. Okay. In fact, we're looking for dy over dx, right? That's the derivative of y with respect to x, but we're actually not going to come up with that function f of x. So when we do so, we need to treat down here y as a function of x. So when I take the derivative of this side, I take the derivative of 2x squared y and the derivative of 6x cubed y. Okay, so we do each one, right? So let's focus on this one. What's the derivative of 2x squared y? Well, 2x squared is a function of x, and y is a function of x, right? Y is a function of x, right? I don't know what it is. Again, I can solve for y here and determine what it is. We're not going to do that, but it's some function of x. So when I have a function of x times a function of x, and I'm taking the derivative, what do I have to use? I have to use the product rule. Very important here. Right? So product rule works like what? I take the derivative with respect to x of the 2x squared times the y plus 2x squared times the derivative with respect to x of the y. Okay. Same thing here when I take the derivative of this, right? I've got 6x cubed times y. So that's a product again. Take the derivative with respect to x of 6x cubed times y plus 6x cubed times the derivative with respect to x of y. So again, product rule here. So I've got to do all that for this side. Over here, I don't have to worry about derivative with respect to x of 3x. That's easy, right? Derivative with respect to x of 3x is just 3. And then derivative with respect to x of y, right? What is that? Derivative with respect to x of y, that is actually dy over dx. And when we say find dy over dx, this is literally, right, the derivative with respect to x of y. It's the same notation, right? So cleaning up over here, the derivative with respect to x of 2x squared, that's obviously 4x, bring the 2 down, subtract 1 from the exponent. Derivative with respect to x of y, again, is dy dx. 6x squared, 6x cubed rather, derivative, bring the 3 down, 18x squared is the derivative. And again, the derivative with respect to x of y is dy over dx. Okay, so we could use this Leibniz notation, the dy over dx notation. I'm just going to simplify things by letting y prime be dy over dx. So what do I have? 4xy, 2x squared dy over dx, which I'm going to write 2x squared y prime, 18x squared y, 6x cubed y prime equals 3 plus y prime. So here's the equation I have after I differentiate with respect to x. And what I'm looking for is y prime, okay? Well, here's y prime, here's y prime, here's y prime. I want to solve this equation now for y prime. So we're done with the calculus part. Now we just do pre-calculus stuff, right? Solving this equation for y prime. So I want to get all the terms with the y prime on one side of the equation and all the terms without a y prime, these two, on the other side. So I'm going to get all the y primes on the left-hand side over here and get all my terms without a y prime on this side. So to do that, I'm going to subtract the 4xy and the 18x squared y from both sides. And I want to get this y prime over here. So I'm going to subtract y prime from both sides. So when I subtract y prime, it becomes minus y prime over here. I have these two terms still, equals the 3 stays here. I subtract the 4xy from both sides and the 18x squared y from both sides. Okay, so I want to get all my y primes over here. Now, what can I do? Well, they all have this common factor of y prime. I can factor it out, right? When I do that, I'm left with 2x squared plus 6x squared minus 1. And y prime times all of this equals this. So to solve for y prime, I just divide by this stuff in the parentheses. So I've got all this stuff here in the numerator, all this stuff here in the denominator. Okay. If I can simplify, I can. And notice, real important, our derivative is in terms of x and y. And that's important, right? Because when we actually look at the graph of this original relation, I'm not sure, I'm not going to show you exactly what it looks like, but a lot of times these relationships will have graphs that, look something like this. I don't know, maybe it looks something like this, who knows? But the point is, for a given value of x, we can have, more than one point on this relation. And this reflects the fact that it's actually not true in this case, it turns out, but in general, it can be that way. So this is not at all the graph of this relationship, but you could have a situation like this. And basically the reason is you obviously y is not a function of x, one function of x, but you can have multiple functions broken up here. It's very difficult, again, in general, to explicitly solve y as a function of x, for instance, because of that. But the point is, the slope is different at all these points. And the thing is, you have the same x value, but different y value. So that's why you need both the x and the y value down here to determine the slope. Sometimes you can express this as a function of x only. But again, this is what we want. A lot of these problems, they'll say just express your derivative as a function of x and y. And that's the derivative. Hopefully this makes sense for you. If you need help, please, as always, let me know.